Example number 6. The definite integral from -4 to 1 of the absolute value of the quantity x squared minus 9 with respect to x equals. So first of all, notice the absolute value. This is different from all the others. We cannot take antiderivatives or even derivatives when we have absolute value, with absolute values. So the first thing we have to take care of is get rid of these absolute values. So remember, this means the integral from -4 to 1 of the function f of x with respect to x. So how do we write this function f of x, which is the absolute value of x squared minus 9, without absolute value? Piecewise. Because remember, the absolute value means the distance from 0, so it will always be positive. Therefore, if I take away the absolute value, it is possible that we have the negative of the quantity x squared minus 9 or the positive of the quantity x squared minus 9. When do those two different expressions occur? Well, let's examine the graph of, first of all, x squared minus 9. Let's make a quick sketch of this graph. Y equals x squared minus 9 is a parabola that has its vertex at -9. It will have x-intercepts where x squared minus 9 equals 0, which is when x equals 3 and -3. So at 3 and -3, the graph crosses through the x-axis. So here is our parabola for the y equals x squared minus 9 before we apply the absolute value. Now, absolute value, we remind ourselves, makes the function positive because distance is always positive. So any part of this graph that is below the x-axis, once I apply the absolute value, will flip over, so positive 9 instead of -9, to be above the x-axis instead of below the x-axis. So what part of the graph is the opposite of x squared minus 9? The part between -3 and 3. So the constraint is when x is less than or equal to 3, but greater than or equal to -3, or between -3 and 3. The part that is the same, which hasn't been flipped over, still this positive portion, is everywhere when x is less than -3 and greater than 3, according to this graph. Now that we know what f of x equals without absolute value symbols, this is what we are going to refer to when we are taking the definite integral from -4 to 1. So looking at this and the constraints, I'm going to start with setting this integral up in pieces. The integral from -4, which is approximately right here, up until just -3, because that's the portion that's the positive x squared minus 9. So -4 up until that first 0 of -3 of the positive x squared minus 9 function. And notice I'm going just up to 1, whereas 1 about right here. So the red graph, which is the part that was flipped over, is the next section. So I'm going to add to this the integral starting where I left off, -3 up to 1 of the negative of x squared minus 9 with respect to x. So if we are doing the definite integral of a piecewise function, we just have to take a look at the constraints to help us know which pieces we're going to use where. Where are we going to break it up? See, the positive piece goes up to negative 3, and then the negative piece starts at negative 3. So I know I'm breaking it up at negative 3. Now we're just solving two definite integrals one at a time. So I will take the antiderivative of x squared minus 9. I get x cubed over 3 minus 9x. Evaluate this one from negative 4 to negative 3. Add that to the definite integral. The antiderivative of this one is the negative of x cubed over 3 and the negative of negative 9x or positive 9x from negative 3 to 1. And then just like the others, we'll plug in our upper limit first. So this first one will have negative 3 cubed over 3 minus 9 times 3. Then plug in negative 4 and subtract. Negative 4 cubed over 3 minus 9 times negative 4. That is that first integral. Plus the second integral. 1 gets plugged in first, negative 1 cubed over 3 plus 9 times 1 minus, now the lower limit, negative of negative 3 cubed over 3 plus 9 times negative 3. And evaluating this and doing our number crunching will ultimately give us 30 if we need to simplify at all.